Hello, everybody. Welcome to the lecture on green chemistry, chemistry within the circular economy, and sustainable chemistry. Maybe you came across with all of these already, and you are wondering, what is the difference? Why do we need the different ones? And what are the advantages? And what are they addressing? This I will explain you in the following lecture for about 40 to 45 minutes. Here a brief overview, the content of the lecture. We will start with chemistry as a science, which is a non-normative approach. That means it's independent of human value propositions, and which in turn means molecules do what they do. We can only change the conditions, temperature, pressure, concentrations, etc., to get more or less the products we want of a chemical reaction. Then we have green chemistry, or better, green not chemistry, because we cannot say absolutely what is green. We can only compare by measuring or whatever means, and come up to a conclusion, something is better than another thing. And this already tells you greener chemistry is a human value proposition. So to reduce waste, for example, within a chemical reaction, that's what we want as humans. Maybe because we want to save money, or maybe we want to save resources, or we want to protect the planet. Nature doesn't care about so-called waste. For nature, it's just chemistry, molecules, materials. And the same holds for a broader approach, chemistry for circular economy, which means how should we do chemistry? How should the products look like that they fit into a circular economy? And that's still not the end of it. We need even a bigger picture, a broader picture, that's sustainable chemistry. How can chemistry contribute in a sustainable manner to sustainability? And one of the most tangible things about sustainability is the so-called Sustainable Development Goals, as set by the United Nations. And above all of this, we have learned there are boundaries, planetary boundaries. So resources are limited. Water can only be polluted, or should better not be polluted at all, if you want to have a safe and healthy planet of the future. The most stringent, or the most important example, most visible nowadays, is the climate crisis, where we have contributed or emitted too much carbon dioxide on a global level into the atmosphere. So all these above this dashed line are normative human value proposition. Also protecting our planet is a human value, because the planet does not care. The planet is just the planet and develops according to the physical chemical conditions and biology. And especially if you go back into the planet's history, there have been many times where there was, in the very beginning, long times no life, and many times where there was only a little bit of life, and life different from the life we know nowadays, and especially life without humans. If you talk about chemistry, we have science, as mentioned already down here, but we have also chemistry as a sector and an industry. And also the sector and the industry are mostly driven by human value proposition, maybe more, better, cheaper, for example, or offering certain functions which we humans want to have. However, chemical industry itself also is rooted in chemistry as a science, but all the applications are normative. So when you think of chemistry or you ask people, normally they think of the products, materials, but non-chemists are often not even aware that all around them, materials, products they are using, laundry detergent, paints, pesticides, toothpaste, personal care products, but also electric car and non-electric car and so on, are products of chemistry, of chemical industry based on chemical science. As a chemist, you probably think about a molecule you want to have here, and then you think about how to synthesize. Which conditions do I need, which starting materials, etc. Maybe you think of a solvent, and that's it more or less. You're normally not thinking about where does the solvent come from, what are the toxic properties, etc. And, you know, each reaction does not completely result in the one and single molecule you want to have. There's always waste, the unwanted side products. So you're mainly interested in the yield of your reaction and not in the waste, or how many of your starting material is integrated here. Nowadays, we have more than 350,000 chemicals and mixtures of chemicals on the global market, which tells you that 150 years of development of chemistry and chemical industry, it's a huge success story. And without it, we wouldn't have our standard of living. If we include pharmacy, which is basically also chemistry, we would not have our status of health and healthy life. However, we also have to be aware that is mostly true only in the so-called developed countries and not in the less developed countries. Here you see some examples of the products of industrial chemistry. So it's literally everywhere: electronics, lights, cars, medicine, cosmetics, furniture, pharmacy, food, etc., etc. But always from the very beginning of industrial chemistry, there has been also a downside of this success story. There has been environmental pollution. For example, if you go into historical sources, then you will find that, for example, the Wupper, a river in Elberfeld, where Bayer Farbenfabrik, a paint and color dye fabrication was located, was for some time, or some long time even, green or red or blue, depending on what has been produced. By the way, this situation we still have nowadays in developing countries like India, Bangladesh, etc., and others, which indicates already we have to think about, has there really been progress? And then always there have been intoxications and also heavy accidents. Think of Seveso. Here you see the Seveso dioxin, the most toxic compound ever synthesized by humans. Or here Bhopal with methyl isocyanate, also highly toxic. In both cases, several thousand people died, lots of animals died, and even nowadays people are impacted in the second or even in the third generation. Here Bhopal in India and Seveso, which is a little city close to Milan in northern part of Italy. Then in the last century, also in the 70s and 80s, one famous example, dumping of waste from chemical industries. Just here in this dumping in the countryside, Love Canal, and a lot of people got sick. And that was one of the starting points of environmental movement and of being more and more aware of the environmental pollution by chemical industries and chemical products. Also, already very early in the beginning of the 60s of the last century, there was a book written by a biologist, Rachel Carson, called Silent Spring. She was afraid of that in future there will be a spring without birds, because at this time we had a heavy use of insecticides, of the chlororganic insecticides, which are, we have learned, accumulating in the food web, which then have been present in breast milk, but also very persistent in the environment. So that's one of the most important books, I would say, as for chemistry, environmental chemistry, and sustainable chemistry, green chemistry. We should have a look into it, because many of the problems addressed there are still around, if not in our so-called developed countries, then in the less developed countries, because we have exported several of the problems. One reaction of this situation in the 60s, 70s, and 80s, persistent products and heavy environmental pollution, was the development of the framework of green chemistry. And that was nicely summarized here in the famous 12 principles. You can see here prevent waste and others. And so summarizing, you could say it's a focus on synthesis and properties of individual chemicals, coming up with less waste, less hazard, less energy, and it also asks using renewable resources. So that was a nice summary. However, the roots of it and the main ways of thinking go back to the 90s. And here you see the link to the pollution, United States of America Prevention Act of 1990. Also in the European Union came into force the Integrated Pollution Prevention and Control Directive in 1996. There have already been included 12 principles for the best to use, and it was asked to use the best available technique. So that was an important point even before we had the 12 principles. But at this time, it was mainly known to authorities and probably in industry and people working there. So the 12 principles of green chemistry, their merit is summarizing the things and getting more attention by time also in academia. By the way, also Gesellschaft Deutscher Chemiker was involved at this time, or the OECD, but also many, many individuals. Not just 2 persons who have later on published these helpful 12 principles. So with the 12 principles of chemistry, we make synthesis and products less environmentally burdening, you could say, and we think about resources. We should use renewable resources, we reduce waste. However, it does not prevent the steep increase of more and more chemicals on the market. And as each chemical and each chemical product at some time in its lifetime comes to an end and may become waste or end up in the environment or in an organism, or even ending up by application in an organism, the question is this approach of green chemistry or greener chemistry, is it really sufficient? And just underlining again, we call it green chemistry, but in fact, we cannot say absolutely what is green. We can only compare, and therefore we should talk about greener chemistry. That would be much more to the point. We should use renewable resources according to green chemistry, the concept. But if you use normal, let's say, or if you use organic resources for organic chemistry, which you have to grow, or for fuel, then you have to be aware that this might be in competition to land you need for farming, for food. And also you need water and fertilizers, which can pollute the environment, especially soil and water. So the best way to do this, use renewable resources called food waste or agricultural waste, as you can see here. Rice husks, for example, straw or orange peels. Some examples here. Then you are on the right track. And that tells you already we have to think a little bit more about the principles, not just calling something green or greener because you use a renewable resource. You have to learn and think about which one you are using. also for resources, renewable resources and synthesis. If we want to go for polyethylene, the polymer, we need to have ethylene. And we can start from the fossil resource, nowadays heavy under discussion. The fossil resource, mineral oil, a fraction of it, naphtha called, it's a non-polar hydrocarbons, as you know from organic chemistry. So there are alkanes and alkenes, the main constituents, also some ethylene already. So we have technical processes, cracking, separation, purification. So physical chemical processes, but also with cracking, a little bit of chemistry. And then we can come up with the polyethylene. Nowadays, we would say we should use the bioresource, so the renewable resource, but a closer look again shows us there are many more steps involved: extraction, separation, purification. And then again, we need chemistry after we have got rid, for example, about the lignin, etc., hemicellulose, if it's from wood, and wood waste. And then we need a depolymerization first. And then we have the sugar, glucose, for example, and this we have to defunctionalize because that's a highly polar molecule, lots of hydroxy group, as you can see here. So we need many, many steps coming from here to ethylene. And each step is a chemical reaction which needs energy, which creates or generates waste. And we can also start with carbon dioxide and water and renewable electricity, which is nowadays often favored. But here again, we need many, many steps. Let's have a closer look. If you think about that polyethylene is a non-polar compound, as is ethylene, why they're not starting with naphtha, which is also a mixture of non-polar compounds, instead of many more steps here, and then the deep functionalization. If we go to polypropylene, PP, similar, here we have it already, or we get it more or less from naphtha, but with a few steps. And if we start here, then we have to think about, we have a branching here, but most of the molecule is not branched. So probably there will be lots of waste. And again, it's a non-polar compound, and it makes no sense, or at least it asks or needs additional steps if we go for non-polar compound, starting with a polar compound. Another example, PET, polyethylene terephthalate, as a polymer and a monomer, it's semi-polar. So maybe here it could be advantages, but it depends on the route. Here, as it's semi-polar, we also need to introduce oxygen. So we had another chemical reaction and another purification and separation steps to come up with this monomer. And also this monomer, we need some defunctionalization. We need here especially build up new structures. Arenes are also part of naphtha. So here oxidation of 1,4-dimethylbenzene could be an approach. And then we have the monomers, and we can go for the polymerization. Maybe here the bioresource could be the better starting point. So that means we have to have a closer and a very careful look, and maybe it depends on reaction conditions and so on and so on, to decide whether this starting point or this one is the better one in terms of being greener. Now let's have a look on the synthesis from carbon dioxide. Carbon dioxide is now often discussed as a resource. And first of all, we have to be honest, using carbon dioxide as a building block in chemical industry would not solve the climate crisis. Because it's not, albeit it's not so much to make a real impact. However, it could be a nice starting molecule because it's everywhere around. And but again, we have to catch it and we have to enrich it, to accumulate. Then we can use electricity or light from the sun and do a synthesis, and then we have all these nice products, building blocks like methane, or you see ethylene after some reaction steps. Again, we have several steps. It's not a direct process. Then fuels, polymers, etc. So this could be an approach to do this. A closer look, however, starting with thermodynamics, tells us already that carbon dioxide is a molecule with very low energy content. And therefore, by the way, it's the final product of each incineration and combustion. So we have to bring up in terms of energy, the low energy carbon dioxide to a high energy content of methane, for example. So we need many materials to get renewable energy, including such as neodymium, dysprosium. We'll just talk a little bit later on this one here. And what we would need in general for this, for electrification and hydrogenation of German chemical industries, that would mean that in a recent study by the Verband der Chemischen Industrie, YCI, of German Chemical Industries Association, there was said we need about 628 terawatt hours of energy, electrical energy, if we want to make if we want to render the German chemical industry green in terms of energy, only in terms of energy, until 2045. However, that's exactly the amount of energy, of electricity, electrical energy, which is nowadays used in Germany. So probably there could be some bottlenecks and limitations, because even if we meet this goal, there will be a further increase, and we will still have all the energy needs we have today for housing, living, for transportation, for communication, and many, many others. So probably that's not a real good approach, and it starts already with thermodynamics, and catalysis cannot solve the problem. Sometimes you read, yes, we can do this better if we start with hydrogen, but then first you have to produce the hydrogen and get the energy for hydrogen production. And also, if we have a look on world oil consumption by sectors, half, more or less, is only by transportation of goods and humans. Petrochemistry here uses about 9% of the fossil oil, and again here 85% is for energy demand. Only 15% here is used for synthesis, though using the carbon as a chemical resource, not an energetic resource. So coming back to which synthesis is perhaps better, starting with renewable materials for polyethylene, polypropylene, maybe at least these we should in the future synthesize by using fossil resources. We should not mix up incineration, combustion of fossil resources, setting free carbon dioxide, and using them in products where there is no setting free of carbon dioxide. What are trends of the future? One trend is that there will be, for different reasons, ever new products, better functionality, but also increase in global population, increase in living standard. This will relate to an increase in resources also. And that's biomass, but also fossil fuels, and also metals. Metals is an important point, and minerals, because these we cannot synthesize. These are elements here. We cannot synthesize them, especially metals. Many of them are already so-called critical resources, as we need more and more, especially for electronics, but also for chemical reaction and equipment. And this relates to what I would call the chemodiversity is also increasing. In it, it's not just an increase in volume. It's expected that until 2050, based on 2010, there will be a fourfold tonnage sales volume of chemicals and chemical products. It also comes along with more different products. And it comes along with products which are more and more complex, containing at the same time more and more ingredients. Here only demonstrating as for elements, mainly metals for electronics. Same with catalysis, and it's often not just a pure compound or a pure metal as a catalyst. Often nowadays we see, for example, nanoparticles containing organic carbon, containing minerals or inorganic compounds, and several or different metals. So complexity is increasing, but also we see just in the sheer number of registered and chemical abstract service a huge increase, especially since 2005. Steep increase. Not all of these will come to the market, but several of them. So its volume will increase and diversity of chemicals. Coming back to what this could mean, just one example for resources. Neodymium, I mentioned already, needed for windmills, but also for all the electronics in cars and all the other electronic equipment. First, we have to mine, not shown here, but that needs already lots of energy and grinding. And then let's have a look on chemistry. You see here lots of steps. You need halogens here, and then there physical chemical separation. And then we have here chemical reaction. The oxide is transformed into fluoride. And then here, that's most remarkable, neodymium trifluoride is reduced by liquid calcium to neodymium. And that's, if you think about that, you need first to get also the calcium as a metal, and then to mold it, to melt it, and the melting point is about 1200 degrees Celsius. And then you have vacuum melting. Yeah, vacuum melting or vacuum generally needs lots of energies, as does increased pressure. So this should be avoided. However, here we have some other issues. Not only that what we want, concentrate the metal, and by the way, in all the applications later on, it's diluted again. We come up with lots of waste, we need lots of energy, and with rare earth metals, we mobilize very often thorium and uranium, radioactive companion metals, which then we have to care for. They are now on the surface of the earth and not safely stored away in the ground as they have been before. This is not addressed by green chemistry principles. Also, metals are not renewable. On the other side, e-waste, electronic waste, even in 2019, about 15 million tons per year, which relates to about 5,000 Eiffel Towers per year, or 7 kilograms per inhabitant. That means quite a lot. And you would think maybe that does not relate to me. I do not need 7 kilograms of e-waste because your computer is not so heavy weighted and you use it hopefully several years. The same for your mobile phone, etc. But all the things in background you have in your car or in your e-bike, the things we need for our infrastructure, for communication, going to the internet, all these is included there. And if you think about that, many people on this planet do not even have access to all these fancy products, then you probably need much more or generate much more than 7 kilograms per year. And also we have learned with this example and many others, environmental, social and economic effects and ethical issues do most often not happen at the place of synthesis or production. Just think of electronic gadgets and equipment. Where does it come from? And maybe a nice link where the photos are also is here. Welcome to Sodom. Your smartphone is already there here. Sodom is a place in Ghana where they do e-waste recycling, or they try to make a living of it. Another trend, as already mentioned, not only with electronics, also with plastics, increasing volume and complexity. So we cannot talk only about electronification, we also should talk about plastification of our world. And you see here on the left side, it starts already at the molecular level of the polymer, different atoms in different arrangements. And then we have not only these nice polymers. If we talk about plastics, very often we have so-called additives in there, modifiers of properties. For example, we have plasticizers or whiteners or fillers and many, many others. You see about 10,000 chemicals in plastics. Here you see a foliage used for packaging of food to keep it fresh for several days. These are 7 layers of different polymers and including also additives. How should we be able to separate this ever and to recycle it? And that's the end of the story. We are well aware of this macroplastics, I guess. By the way, most often not happening in our countries where we are using them, where we are producing them, but in other countries. So they do not have the issue of environmental pollution by waste of production. Still, they are also now confronted with the end of life of our products. And they are using them also too. Yeah. And then these are often broken down during their lifetime in the ocean. Then we get the micro and the nanoplastic, which is another challenge for the safety and health of this planet. And by the way, just skimming it does not really solve the problem, because 2/3 of the plastics has already sunk down to the floor of the sea, and we will never get hold on it. So that's irreversibly changed already. With the shortage of resources, which I have not so much mentioned, but I think with the fossil oil, it's clear, but also with metals and other elements, phosphate, phosphorus, we have on the one hand the shortage of resources, on the other hand we have at the same time lots of waste we are generating. So it's quite normal to think about circular economy, so circulating products and also recycle them if they come under the end of life. Please be aware, circular economy is about both circulating maybe as long as you can without losing as little as you can, but also then at the end of life, recycling, that is to get hold on the constituents of the products. Again, that's a human value proposition. Yeah, circular is better, and the products are here in the focus. To enable chemistry and its products to contribute or to be compatible with a circular economy, we have to think about a few things. We need to reduce complexity of the products, but also of the total materials and substance flows. Yeah, they are often mixed products after they have become waste, yeah, not separated, or even if separated, if you bring your goods to the recycling, then you see, yes, there are metals and there are plastics, but within these, we have still a huge mixture. Even if it's metals and electronics, there are still plastics and so on. Yeah, we have to reduce toxicity. About 60% of volume used in the European Union of chemicals for products is still highly toxic, even nowadays. And we have to design for little loss, because if we circulate things, then always something is lost. Not lost in terms of, for example, that metals are not there anymore, but there are maybe in very low concentrations somewhere along the roadside, also from a catalyst of a car, and then we have not enough energy or money to bring them back and to use them again. So we have also losses by entropy increase. And the more complex products are, the higher this will be. So we should avoid complex products and keep the complexity to a minimum. and should also not change it then later on. That means minimize use of components, minimize mixing, because each mixing needs again energy and generates waste when I want to separate it and grade up products. We should design products from the very beginning for recycling, and product already could be a molecule or a mixture of molecules. And the same holds for processes. We should keep products and processes as simple as possible. So the most elegant way is not to demonstrate all the fancy technology involved there. The most elegant way and the best way is to keep it simple. KISS principle, you could say, keep it simple and thereby sustainable. So we need products and which are more sustainable by design. And that means we have to think about molecules, materials, and products from the very beginning, because it's not just the individual molecule or material. In the end, in the economy, they sum up, they are mixed, etc. And we should also have a broader look in terms of avoiding rebound effects. For example, if we go for low carbon energy, for example, often means high metals. So maybe nothing is gained or situation is even worse. As already mentioned, we should reduce and simplify diversity and dynamics of the substance, materials, and product flows on local, regional, and global levels. And we have to be responsible for what we are doing along the complete life cycle, not just along the value chain, because the value chain ends where there is no value anymore. And to better understand, we need also appropriate metrics, including use of byproducts and circularity. And most important, maybe we have to change our traditional thinking based on bigger, faster, more complex into optimal, adapted, better, safer, and less complex. Then circular economy, then chemistry fits into circular economy and can make a good contribution. However, again, just to mention it here, there is neither endless recycling nor so-called upcycling. Some people say, yes, we can upcycle. No, you cannot upcycle. Yes, you can increase the grade of a metal, for example, but then you have a lot of slack, and that's waste. And maybe if it's not considered, then you can say, yes, we have another high-grade product here. But even with steel, it's not possible. We also always need fresh material, because steel is an alloy, and we have about 600 alloys, 600 types of alloys, steel alloys on the market. Each has a different composition. So we have to dilute within recycling to be able then to add targetedly what we need to get the old quality again. Also thermoplastics, if you remold them already, quality goes down. So there's always a price. That tells us also thermodynamics. If someone there's an upcycling, that's not true. Even if you take a material and you make bags of it, yes, maybe there's one more cycle. Or if you regain phosphorus from sludge, yes, it's one more cycle, but it's only one cycle with lots of energy needs, and it's not an endless recycling. And we also have to be aware that not all chemicals and products can be recycled. Just think of your shampoo you have used this morning, for example. Here we can contribute with a solution by the 10th principle of green chemistry. So molecules that go to the environment have to be designed from the very beginning for environmental mineralization. Here's some examples from our work. Important, what's reflected here is the thinking is think from the very beginning already at the end of life. The end already always in mind when you start, and not only at the end thinking about when the problem is there. What we need, in fact, is a much broader thinking and understanding, which is so-called system thinking, because sustainability and greenness depend not on individual points or technologies. We have to look on the whole system, what is really a better contribution. The whole system we have to take into consideration. So the bigger framework is sustainable chemistry, which we need, or chemistry for sustainability. It starts with a service. It asks first what is needed, which service. Yeah? And often with a better construction, for example, or selecting a better natural material, you do not need additional chemistry. For example, if you have a facade, which is thermally insulated, often fungi and algae are growing there. However, if you use wood, for example, or if you have a roof which prevents the excess of water, then there will be no growth or less growth. That's just one example. I'll show you later on a few other so-called alternative business models. So then we can think about the function we need and how this can be done without chemicals, or if there are chemicals, then with less chemicals and better chemicals. That's very important. And we also have to include stakeholders, ethics, and social aspects. Where do the resources come from? The metals, for example. If you think about the artisanal mining of gold, or the mining of cobalt in the Congo by child work, etc. But again, sustainable chemistry is also a human value proposition we have to be aware of. And what's important here, also nicely demonstrated, not everything which is greener fits automatically into a circular economy and fits automatically into the framework, the big framework of sustainable chemistry. And the same holds even if it can be circulated, not necessarily it contributes in a sustainable manner to the sustainable development goals. So here we have the complete picture of chemicals and chemical products, the new thinking, chemistry for sustainability, and the role of chemists here. Service and function is the starting point. And then we can design systems. And within the systems, we can design them, synthesis, resources, but most important, first of all, the products. How should, starting with end of life and use, the function, and then we can think about how should they look like, what should be the properties, and then we can bring this down, and there we need all our chemical knowledge, how to best meet a product's properties to meet circular economy and other issues during its life cycle, and to allow also recycling. Recycling is only the latest. Third, we should start for using as long as possible, then for disassembling of building blocks, or with plastics, for example, we should use thermoplasts for remolding, yeah? And only then, only at the very, very end, we should go for depolymerization, for example, or we should apply metallurgy. That's very challenging and hard for chemists, because chemistry is on the synthesis of new materials, new molecules, but the future is different. The future would ask us to be more humble. Only if it's needed, we should think about. And then we are needed with all our knowledge to make it better than in the past. But first of all, we have to be humble. Else probably we will not be successful in the future. And interestingly, often it's feasible doing better without. For example, we are working, and now my working group, with making silicones better environmentally compatible. When we started this work and talked to industry, they said, we can never afford products, for example, shampoos, conditioners, etc. Shampoos and conditioners without silicones. Nowadays, you enter a drugstore and you see shelves with products advertising silicone-free. And interestingly, from an economical point of view, the products are not cheaper. Less is in there, less has to be done and invested and paid on the production side, but the products are not cheaper. They're even more expensive. So with less, you can make even more money. Same for food, no artificial flavors, synthetic colors, or preservative. So it's possible. It's just a matter of mindset. Also within chemistry, since years, several years already known, the so-called chemical leasing. What you're interested in is not to possess a solvent. What you are interested in is to use it, to apply it, to dissolve your compound, and then to get rid of it. And as long as it's just waste, you are not interested anymore. You are interested only what might it cost. But if it's leased and you give it back after usage, like a car, then maybe you can save money if you think about how can I go with it, with that it's less polluted in the end. Or you talk to the company which has leased the solvent to you, how can I do better? So both of you talk to each other more intensively and come up with a better contribution, better and savings also for both sides. So here the thinking is from business model, from increasing the sales volume of a chemical, it's towards a value added approach. You are paying by the functional unit or by the service. And there in this UNIDO brochure, there are many, many interesting examples of this. Yeah, now coming back to the broader picture again, United Nations Sustainable Development Goals, which I have mentioned already several times, and chemistry. Chemistry is involved, if you have a little bit of more broader view in the sense of sustainable chemistry, as mentioned, in all goals and in many specific targets which are related to the goals. So there will be no sustainable development without chemistry, but it has to be a better chemistry, a more sustainable chemistry. A greener chemistry is only a building block and only in case. That's not enough. We have to go for the broader picture. And then we can also meet and cope with the boundaries of our planet. There's this concept of planetary boundaries developed by Rockström and Steffen. And I think it's quite clear the volume and the surface area of a globe is limited. And that's it about. So they developed a nice approach to see where we are already coming close to this planetary boundaries, what we can afford, what the planet can carry. And interestingly, you can see here we have nothing. It's called noble entities. With synthetic chemicals, maybe because it's so many and all behave different, each is individual, maybe it will never be possible to define a so-called boundary where we are on the safe side and the safe operating space. Therefore, in general, we have to reduce and to do with less chemicals for better service. So that's in a nutshell about green and sustainable chemistry and how chemistry could fit and could contribute successfully, not only in terms of economics, but real successfully to the service of humankind, to a circular economy too. At Lüneburg, we have developed, for example, a master course, an extra-occupational one you see here. We'll not go into details, but the point is we are teaching chemistry. That's what you normally, as a chemistry student, have. Chemistry is taught, maybe green chemistry a little bit, and environmental chemistry we have included, basics of toxicology, ecotoxicology, how to design better chemicals. But we also teach about chemistry. How does it fit chemistry into the real world, into society, economy, but also you see here responsibility, business models and strategies, but also law. Chemists have to know more in the future. And the same thinking we have in our Master of Sustainability Science. Summarizing last slide here, sustainable chemistry is the awarding, that's important to understand. It's really awarding, as you have seen with alternative business models. You can even make money with new molecules in the future, which have better properties. You have new business opportunities. So sustainable chemistry is in each respect, including economical ones, an awarding approach it's an inter and transdisciplinary approach. It's based on system thinking instead of punctual solutions. Thank you for your attention.